Hi there. I'm going to just make some comments, especially in comparison across systems. Um, there are a lot of aspects of performance. Ideally, every time you talk about performance, you would cover each of these in intricate detail, but that's not very realistic. I tend to think of these as being grouped. CPU cycles, memory bandwidth, NUMA tend to be specific to the CPU model and the configuration of the host. GPU, flops, and interconnect, again, specific to the particular GPU type and how it's interconnected, for which we have some variety across hosts. I'm probably not going to talk as much about GPU, unfortunately, just because there's a lot of other things to talk about. The internode network is very important if you're doing things like MPI. To some extent, it also affects Lustre performance. But since we have 100 gigabit networking as our internode network on all the systems, that's less of a factor for Lustre. Local storage is important. You may not be aware of it, but there is a storage local to each compute node, which is much faster than you can expect from remote storage. And I'm not sure I'll have time to go into details on that. So performance you experience depends on many of these factors, and in general, it's the minimum of any bottleneck in your program, which is really unfortunate because you may have excellent scaling on one aspect of your program, but if the other is poorly tuned with respect to the hardware you choose, your overall performance will be poor. Many of these metrics are shared resources, which means that it's difficult to get good measurements on them. So, for instance, if you're doing by node, by core scheduling, then you'll be competing for various node resources with other jobs that happen to be on that node. Even if you choose whole node scheduling, you'll be competing for factors like interconnect and Lustre. So in my approach, I tend to just measure real performance without quiescing the system. In fact, sometimes I'm stealing cycles from people who are running on nodes. And the logic there is just, if you were running a job, what performance could you expect given everything else that's going on in the system? I like to start with the theoretical specs. So this is something I'd never really done before. It's a rack up of all of the CPUs we have in Compute Canada. So this is counting Cedar, Graham, Niagara, and Beluga. So it's not counting Narwhal. It's not counting some of the smaller or specialized systems. So I didn't realize exactly how much we'd focused on these things, but we have quite a large number of particular processors. And some of the processors I've highlighted as being particularly attractive. Basically, so if you look at this, you'll see that there are some processors which are pretty old. So for instance, first quarter 2016, that represents the set of systems that we installed uh, about 5 years ago. I guess about 4 years ago. And they tend to have somewhat lower specs. So since then, we've installed quite a few newer processors that have nicer specs. So let me just decompose these lines a little bit. The left column is, of course, the number of processors. Then there's a model name, which is somewhat marketing oriented. And just for kicks, I put in when Intel said they introduced the processor, since that's sort of an interesting reference point. Then how many cores per socket? So normally we have 2 socket nodes, so the number of cores per node is twice this value. Then the clock frequency range, which is pretty interesting. The amount of per socket cache, and then the theoretical bandwidth per socket again. So I find these numbers pretty interesting. especially because there's a 2-to-1 range, which is pretty impressive. So for instance, if you get on those 761 Xeon Platinum 2860s on Cedar, you can expect substantially higher clock rates and more memory bandwidth than, for instance, the Niagara nodes, which are in the range of 70 gigabytes per second. We also have smaller numbers of other things. I just picked out in green the newer generation nodes that are on Graham. Yeah. So I guess this slide is a little bit out of order. So if you look at this table, you'll see that there is a range of clock rates available. The first lowest clock is what's normally referred to as the base clock, and then the higher end is a burst. The burst is achievable under certain circumstances. Most of these systems are potentially thermally limited, but that Xeon node in the middle there, for instance, can go up to 3.7 gigahertz. That's a pretty substantial boost, almost twice as much as the base clock. So in this table, I've just got the measured clocks for every core. No, this is the maximum clock on each node of 3 different systems. So here's Cedar, for instance. Cedar is configured to avoid bursting. So most of its nodes are configured to run at their base clock. And you can see this, this line in the middle, which is at about 2100 megahertz, is most of the nodes. And then there are a few nodes whose base clock is at 2400. And Cedar has a few nodes that they allow to burst as well. I found this sort of interesting because nodes that are idle will actually have much lower clocks, and you can see those at the left-hand side of the plot. Here's the same thing for Graham. You can see that on Graham, even though most of the nodes have a base clock of 2.1 gigahertz, most of them are actually bursting substantially above that. And some of them are bursting to the roughly around the 3.7 gigahertz, which is the maximum. And then Beluga is actually much more aggressive in bursting and also has a uniform set of nodes, which are newer. And so all of its clocks burst at near the maximum clock speed, which I think is quite interesting. I'm just going to go straight on to interconnect specs. All clusters have 100 gigabit interconnect. In general, the GP clusters are what we call fat tree, which really means that there are subsets of nodes which are in fully connected islands. That is, they're plugged into the same interconnect switch. And then those islands are fed through multiple links into a higher level switch. So the effect is that if you land on nodes which are on a single island, you'll have much better performance. But I was a little bit surprised at the measurements. So for instance, here is Beluga. This is on 2 nodes, as you can see in the caption. I think they're in the same island, but I'm not completely sure. The numbers are close, so they're probably in the same island. And I think this is a very interesting graph because, so it's a histogram of the latency. I think this is the full round trip latency between 2 nodes. So the expectation here is that InfiniBand generally has advertised at about 1 microsecond latency between nodes. So the round trip latency for a ping pong should be about 2 microseconds. And one of the interesting things I thought about this is that there are a significant number of outliers at the top of the graph. Now, there's still, only 10 microseconds. It's not, like packets are getting lost in the network and never finding their way. But if you're not expecting at least a few high latency messages between your MPI nodes, this might be a shock to you. Here's the same thing on Cedar. And I have to say, this really surprised me because Cedar's interconnect is different, but should have similar specs. So these numbers are substantially higher. You'll see that, the peak of the histogram is more like 3, maybe even 4 microseconds. And there's a fairly substantial set of outliers all the way out to 10 microseconds. This also surprised me. So one of the cleanest curves is on Graham. And I should say that all of these are, as far as I know, nodes that are in the same island. So here you have basically 2 microseconds, very clean power law distribution, very nice curve with not much in the way of outliers. And just for comparison, if you run the same MPI ping pong test across a single node, you might be thinking, well, the interconnect is a big bottleneck for us. But it turns out that this is not touching the internet. So this is using shared memory to go between 2 processes on the same node. And its latency is not that far from internode latency. So this is maybe 1.5 microseconds versus 2.0 or 2.1 for a full internode. I'm going to roll right on to storage specs. It's important to note that the local disk is an SSD, but it can range from a SATA disk in some of our older nodes to NVMe, which all test out at about 2 to 3 gigabytes per second. Lustre and GPS can certainly be fast. And the real performance of nodes tends to be quite noisy. So I wanted to show you graphs here, but it turns out the graphs are not really that interesting. If you just do pretty much any bandwidth test on project, on Cedar, Graham, or Beluga, you'll get about 1 gigabyte per second using my methodology, and about 3 gigabytes per second on Niagara. Now, Niagara is obviously the premium cluster. We know that because it has a very large number of uniform processors. It has a very clean interconnect structure, and it also has quite fast file systems. We have to say that. So in some sense, IO intensive operations should go to Niagara as well. For GPU specs, like I said, the topic is quite complicated. I thought it best to just show the spreadsheet I have. This is a spreadsheet of all of the GPUs we have available within Compute Canada. I suppose I can share this publicly. And it breaks down all of the performance considerations. So for instance, you can probably ignore the K20s and K80s. Those are on significantly older clusters. P100s are quite common. V100s are quite common. And the new incoming Narwhal cluster will have A100s. They're at the bottom. But even among the V100s, which you can get different varieties on different clusters, there are some fairly significant differences. So for instance, the V100S model, which is available on some systems, has a fairly significantly higher memory bandwidth. And you can see generational shifts between the GPUs available for the P100s, for instance, available on Cedar and Graham. They have pretty respectable FP64, that is 64-bit floating point, noticeably lower than V100, but still in the same range, so 5.3 versus 7.7 or 8. And a similar ratio for 32-bit. But the big difference if you're looking for V100s is that they've got tensor cores, which means for a particular very restricted matrix multiplication operation, which is used primarily by AI, there can be much higher throughput. So for instance, they have 640 tensor cores, and they deliver around 120 gigaflops. I think that's gigaflops of TensorFlow 32-bit TensorFlow operations, which is an entire order of magnitude higher than the raw floating point 32-bit floating point operations. And this trend actually accelerates with the A100s, the upcoming A100s. You can see that there are a very large number, very high throughput of TensorFlow gigaflops, especially compared to the conventional floating point ones. I wanted to present some information about GPU interconnect, but in the end, I sort of threw up my hands because it's very hard to get good numbers on this. There are tools which will show you. I guess my conclusion is basically you get a node and you can measure its interconnect, but attempting to design your job around which interconnects are available is sort of a mistake. So for instance, we have nodes with between 4 and 8 V100s on them, and they're connected in pretty much every possible way. And really your best bet is just to do some measurements of your own application. There is a tool installed on the clusters which does a pretty good job of measuring, at least giving you an idea of what your hardware configuration interconnect bandwidth will be. And that's probably the best thing to use. That's bundled with CUDA. It's called bandwidth test.